Good morning, or whatever time of day it happens to be that you're there. But for me, it's the morning. I want to finish off Chapter 9 with you guys and trying to be taking into account our scheduling for the AP exam. Well, in this chapter, we've been talking about orbitals and covalent bonds. And how did that work? We talked very quickly about how atoms that they would bond together with their orbitals. And we know about orbitals, the shapes of orbitals like this. But then when you start getting into what happens when you combine them together, and we had some models here about how these things come together. This should be a quick review for you guys. But the truth is that the orbitals themselves, they don't work. And it has to do with the valence electrons of carbons. There should be 2 in the S and 2 in the P. Carbon has 4 valence electrons, so in theory, the P orbitals should be at right angles to everybody else, and guess what? They're not. So what's the evidence that it is? It tells us that the atomic orbitals, they do definitely change. So that's when we started to talk about the idea of hybridization. We looked at the idea about the blending of the S and the P orbitals of the valence electrons, and that's how they ended up with the tetrahedral geometry of the CH4. So when you look at this picture here, you should be following along in your notes. You should be seeing where the 2s, the 2p in the x, 2p in the y, 2p in the z, okay, they all hybridize together to form this sp3 orbital. And here is CH4 with this idea of this, how these orbitals are hybridized and how they come together. So when we look at something like the localized electron model, this is one way we try to explain what is exactly happening here, where you have your S, your P's here, PY, PZ, PX, and when they combine and they hybridize, look how they turn out. They sort of turn out like a mushroom in a way. We talked about molecular orbitals. We talked about the idea of molecular orbitals, and we said about it's the overlap of atomic orbitals from the separate atoms. That's where we get these molecular orbitals, because remember, if you're combining 2 atoms, you're getting a molecule out of it. Now, of course, each of these molecular orbitals only have 2 electrons. So there's 2 types of molecular orbitals. One is the sigma, okay, and the other is the pi. Now, the sigma is directly in between the atoms themselves, whereas the pi, it's up and down, it's above and below, and you can see that here. And this would be our sigma bond. We don't call them MOs, we simply say sigma bond or pi bond, but the sigma bond is a single bond between 2 atoms. The pi bonds are dealing with the p orbitals that are separate, okay, and they are above and below the atoms. So it's kind of weird to picture this. We talked about what would happen if you look at s orbitals on separate atoms. You kind of notice that there's this sigma bonding. There's this hybridization that happens. When we look at the p orbitals, you kind of notice here that sigma bonding, again, between 2 atoms, okay, of the molecular orbital, that these 2 p orbitals, they come in together, and this is what we're seeing. This is what they're forming. Now, what about the p orbitals that are on the separate atoms? Okay, well, here's the thing. If you look at it, they get together, and you notice that they sort of hybridize in a way. There is that pi bonding molecular orbital. So in other words, the electrons are able to jump around going this way as well as going this way. So there's a certain amount of freedom that the electrons have. And again, how is it that we know about this? Again, it's the behavior. It is the behavior that these atoms are displaying, and it's research again and again and again. And there's still things that are not completely set as law in the chemical community, in the chemistry community. It's just not happening. So all the single bonds are sigma bonds. Double bond is 1 sigma, 1 pi bond. A triple bond is 1 sigma and 2 pi bonds. This has got to be one of the most important of the slides here for this chapter. Okay, that would be kind of an important thing for you guys to see. Sigma bonds are single. Double bonds, it's 1 sigma and 1 pi. Now remember, the pi bonds are not connected directly to the atoms like the sigma bond is. The sigma bond is in between the 2 atoms. We're looking at two carbons here, for example, whereas the pi bonds, they are above the atom and they are also below the atom. So if we look at a single bond is sigma, a double bond is 1 sigma, 1 pi bond, and a triple bond is 1 sigma and 2 pi bonds. Now if we looked, we talked about the idea about in terms of energy, we noticed that the sp3, it's a little bit lower in energy. We talked about that. And the reason why it's a little bit less energy here, it has to do with that stability. You're taking the 2s and the 2p and you're combining them. So that's why you have a little bit less energy there. And remember, less energy means more stability. That's another key idea here. Okay? How did we get the hybridization experiment? We already know the orbitals of the atom, and by hybridizing these atomic orbitals, it gives us a clue about the geometry. So if the geometry requires a tetrahedral shape, we know it's sp3 hybridized. Now this sp3 hybridized can also include bent, trigonal pyramidal molecules, because one of the sp3 lobes holds the lone pair of electrons. Okay, so here's sp2 hybridization with C2H4, and you might get the idea about that carbon is double bonded with itself, and then the H's are sticking out at the ends, 2 on each end of the carbon. So you have the double bond that'll act as one pair. It's a trigonal planar, okay? You have to end up with 3 blended orbitals. So how in the world do they explain that one? Well, they used 1s and 2p orbitals to make this sp2 orbital, which means that there's 1 p orbital that is actually perpendicular to this. So this is what it would look like. We have the px and the py with the s, and now we're combining them together. So this is what you would get. The s with the px, the s with the py, okay, sorry, the s, yeah, it's just looking at it at another angle. Okay, you're looking here in the x, and you're looking again along the x, you see what the other side looks like, and then here is the s with the py. So you're getting an idea about this conversion. Now, your notes don't contain everything, because it also includes and, bam, hybridization. That is the sp2 hybridization that's there. And again, we look in terms of energy, guess what? Ooh, it's a little bit less in energy compared to the 2p and the 2s. And again, why is the hybridization having less energy? Promotes stability. Remember, you're combining. I talked to you guys about how hybridization is kind of like a marriage between a man and a woman. Okay, that there are changes that both will make because they are hybridizing, that they would become one. As it says in Genesis, the two shall become one flesh. Now we're on the new stuff here, and I'm flying through. Where is this PZ orbital that they're talking about? Well, it's perpendicular. So if we have our sp2 orbitals here going along the plane, the PZ orbitals are going up and down, okay? And that overlap of these orbitals, they make the sigma bond. And that's what we're seeing right here, okay? So we've got a sigma bond here. We do have sp2s here and here as well, okay? And there is a bond definitely with the hydrogens. That should not be a big surprise there. But remember, there's 2 types of bonds involved, okay? There's sigma and there's pi. Sigma bonds are formed from the overlap of the orbitals, not like the pi. The pi bonds are formed, the pi bonds are different. They are above and below the atom, but the sigma bonds are in between the atom. That's where you get your single bond. When we look at the pi bond, it's above and below the atom. Now, they happen to be adjacent to the p orbitals here. And that is the 2 bonds of a double bond here. Okay? So that's the 2 bonds of a double bond, which is what you're seeing here with the carbon. Because for one bond, it's 1 sigma bond. For a single bond, it's a sigma bond. If it's a double bond, it is a sigma and a pi bond. For triple, it's sigma and 2 pi. Now in this case here, we look at these 2 carbons, we have our sigma right here, but we also have a pi bond up here. You'd say, but wait a minute, why don't we have another one down here? Well, the carbon's not triple bonded. Wait, how do we know that? Well, remember that the carbons here, they have 4 valence electrons. Okay, and we are looking at the C2H4. So, if you think about it, the carbons, they want to have their 8 electrons. That's part of that stability thing. Okay, so when we look here, here's our double bond, and here's the double bond that we have. Here's our sigma bond, here's our pi bond. And notice in green here, our sp2s, those are the hybrids. Those are the hybridization of the px, py, as well as the s. So what is it that we have at the end? Well, we have our 2p as well, and that's where we see our other pair of electrons. So here that shows us we have a double bond right here. 1 sigma, 1 pi. And then of course we have single bonds, or sigma bonds if you will, between the hydrogen and the carbon. Okay? Now, sp2 hybridization, as we continue, we got 3 electron pairs around the atom. The shape is going to be a trigonal planar. Now there's going to be a 120 degree angle between the atoms. And again, 1 pi bond and a sigma bond and 1 lone pair, that gives us 3 pairs around the atom. Okay? That would be kind of an important thing. Now, what happens if you got 2 electron pairs? Okay? Well, when you have 2 electron pairs surrounding the atom, 1 s and 1 p will actually hybridize. And that's going to give us a linear molecule. So here's our s, and let's say it's our p in the x direction. When they hybridize, this is what you're going to get. Okay? Now remember, the idea is that, yes, you see them as separate, but remember to combine them together, and that's what we're actually seeing. So in other words, are you going to be seeing some overlap? Yeah, absolutely you are going to be seeing some overlap. That's true, but remember, these areas, compared to the size of electrons, they're giant, they're huge volumes of space. That's a huge thing. Okay? Now let's take a look at sp hybridization. We've looked at sp3, we've looked at sp2, and now we're looking at sp. Now with sp hybridization, okay, we look at 2 lobes, okay, and a lobe, you could think about the lobe in your ear, or you can think about the lobes here of the p, okay, or you can look at it, the sp as the lobes. Now those are 180 degrees apart. That makes sense. Remember the valence shell electron pair repulsion theory, that the electrons, they want to push away from each other as much as possible. So if you have got 2 lobes, they're going to be at 180 degrees apart because they want to be as far away from each other as possible. Now the p orbitals, yes, they are at right angles. Now what does this mean? It allows room for 2 sigma bonds and 2 pi bonds. So you could have a triple bond or 2 double bonds. It depends how many electrons are there for that. Because remember, for a triple bond, you're going to need 6, which means 1 sigma and 2 pi. If you have a double, you need 4 electrons, 1 sigma and 1 pi bond. Okay? That would be the difference. And again, if you look at in terms of energy, look what happens with the sp. Now notice it's not happening with the 1s, all right, because there's no hybridization that's needed there. The hybridization's taking place starting at level 2 and going up, because now you've got more than 1 sub-level in that energy level. So here you've got sp, and again, it's a little bit lower in energy compared to the 2 p's, and guess what? Less energy means more stability. All right, let's look at carbon dioxide. Now CO2, we know it's a double bond with the carbons and the oxygens. So here the carbon can make 2 sigmas and 2 pi bonds, whereas the oxygen can make 1 sigma and 1 pi bond. So what is that going to look like? Well, here's our carbon. Carbon's going to be our central atom, which is very typical. Here you've got your one pair of electrons there. Those are your sigma bonds. Right here, these are your sigma bonds. Now when you start looking here, when you look at these pi bonds here, ladies and gentlemen, guess what? Those are your double bonds. Now you'd say, but wait a minute, you got these dashed lines here and up here. Well, remember, there's a possibility to make a triple bond. And that's just what it's showing. But in this case here, you know, they would just show that the electrons would be up in this way and up in this way here. Does it matter if the electrons are down here or up here in terms of the pi bond? No. No, it doesn't. But when you look at it, here's your carbon atom by itself with its sp hybridization. Here is oxygen with its sp2 hybridization. So when we look, okay, how they combine, now we have a better understanding about what's going on here. Okay, and N2, we're going to move on here. So N2, it's a triple bond where you're going to have an sp hybridization, and here you have, excuse me, sigma bond. You have a lone pair here and a lone pair there, okay, and then you have your p orbitals, which again, if you look here and here, they're going to form your triple bond, and that's what it would look like. Okay, that's how we see the nitrogen molecule, which, remember, that makes up most of the air that we breathe. My time is running short. Breaking the octet. You've heard me talk about breaking the octet before. Now, I got to point out something like PCl5. It predicts we have to use the d orbitals, and that's where you get the d sp3 hybridization. Just get an idea what is this, that it's a hybridization of the s, the p, and the d. It's still controversial. They're not making a big deal about it in the science community. I wouldn't worry about that too much. Localized electron model, the DSP3, okay. Trigonal pyramidal can only sigma bond, cannot pi bond, basic shape for 5 things, like, for example, PCl5. So when you look at it, this is what these regions look like when they're all connected to each other. And assuming an sp3 in order to minimize the repulsion of the electron pairs. Oh, goodness. Okay. Localized electron model, D2 sp3. How high does this go? Actually, there's a limit because there's only so much that we can figure out. Now, in this case here, we can look at 6 things to go around the central atom. It would be octahedral, which would be 8-sided. And they only sigma bond like the SF6. And this is what you're seeing here, despite that you've got these hybridizations that you're seeing here. As we're wrapping up, okay, this is using the localized model, the localized electron model. And it tells a lot of things about bonding, but as models are, there are limits. It isn't going to explain away unpaired electrons. It's not going to explain away bond energy, which we talked about earlier, and it's not so good with resonance either. Remember resonance, where you can have a single bond here, a double bond here, and it can switch like that. This is resonance, okay? And again, we're not going to go there. This is the end for Chapter 9. And like I said, I wanted to take the time with you guys to spend, but I do need to move on, and I needed to conclude this chapter rapidly. Remember, there's no math here. It's pretty much the theory, okay? And why do we bother to use these electrons, these hybridizations? It explains things as far as bonding between atoms. Okay, guys. It also helps determine the shapes of the molecules, the geometry. Okay, guys, I'm hoping this is helpful, and I'll see you the next time.